Thank you very much to the organizers for inviting me here. It's a great pleasure to talk about our work. So this is work done with Margarita Davidova, Nat Tanti Vasadakaran, and Shankar Balasubramanian, who are at MIT, and Caltech. And the work was heavily inspired by recently developed Floquet codes, in fact, initiated by Hastings and Ha, who are in the audience today. And the idea is to sort of combine components of sort of lattice surgery-based methods in like Tor code and transversal gates of, that exist in color code so that you can sort of get both properties simultaneously. So we want to find codes that are both error correcting while we compute at the same time. And these dynamic automorphism codes give you an efficient way to do that. Okay, so the outline for the talk today will be first some introduction, motivation, reminder of toric code. From there, I'll go on to review the Hastings and Ha code, which is pretty essential to this discussion. And then I'll review some results by Kesseling et al. About anion condensation, color code, and the Hastings-Ha code. And then I'll start discussing our results. So from there, we define something called the condensation graph, which one can use in order to design these dynamic automorphism codes. And I'll give a few explicit examples, namely the dynamic automorphism color code in both 2 dimensions and 3 dimensions. All right, and of course, feel free to ask questions at any time. Okay, so first, let me review the toric code. So probably everyone is familiar with this code. It can live on, well, actually any dimension, but today just in 2 dimensions. And I'm going to put it on the square lattice. So we put 1 qubit per edge of this lattice. And we have a stabilizer group, which is generated by the following operators. There's a Floquet term, which has Pauli x around its boundary, and a vertex term, which has Pauli z around the vertices. And just in case anybody is not familiar, x is the operator just like this. Z is 1 minus 1, and on occasion we'll use y, which looks like this. Okay, and so this stabilizer group defines a topological code, which means quantum information is stored or distributed non-locally across all the qubits, and no local measurement can have any access to that information. The logical operators are given by any operator that commutes with S, which is not in S. And we denote that by S perp mod S. In this example, they come in 2 flavors. So there are direct lattice logical operators, which consists of product of x on all edges they cross. So it's just some path of edges. And then there are dual lattice logical operators. So taking a path across the dual lattice, which consists of Pauli z every time they cross an edge. These 2 logical operators anti-commute. Call that x bar. We can call this z bar. And if you're on a manifold with non-trivial topology, you'll have a non-trivial code space. All right, so hopefully that's a review. Now, sitting inside your quantum hardware, you don't always have access to measurements like this. So a natural question is, how do you realize that? And there's a well-known way to do this, which looks like the following. So we put 1 ancilla or auxiliary qubit on every vertex and 1 auxiliary qubit for every plaquette. Here, I'll draw what the vertex 1 looks like. So we have some auxiliary qubit there, and then 4 qubits that sit around it. And then we design a quantum circuit that measures the vertex term vertex term associated with that vertex. So auxiliary qubit here, 1, 2, 3, 4, 4 control knots, like so. And then we measure in the z basis at the beginning, z basis at the end, the difference of these two eigenvalues tells you the value of that weight for Pauli term. Okay, and as it turns out, there are many ways to design such circuits in order to measure into the surface code, for example. And part of the magic of the Floquet codes and these recently developed pairwise measurement codes give us new ways of actually measuring into these topological code space. So over the last 2 years, there have been many developments in how to do this. So first example in recent years is the Hastings-Haw code, which I'll review momentarily. We had one, me, Jang-Han, and Matt, called the EM automorphism code, which is again a sequence of single Pauli and two Pauli measurements. There's a so-called CSS honeycomb code, which was proposed here and also separately by the three co-authors there. There's the pentagonal code of Gidney and several fracton codes, which have also appeared. It's a very interesting and quickly developing subject. Okay. All right, so why would we be interested in pairwise measurements? Well, one reason is certain hardwares actually have these measurements natively. So I work at Microsoft, and in Majorana-based hardware, pairwise measurements are native to our architecture. So that's one reason why we would be interested in them. There are also very interesting codes to just look at independently. All right, so with that, let me review the Hastings and Haw code. Hastings-Haw honeycomb code. And I'm going to spend quite a bit of time on this because Hastings. Because the examples that we give, the two-dimensional dynamic automorphism color code, is really a direct generalization of this. So, but it's also much more difficult to draw the pictures in that case. So I will describe what's going on there, but often refer to the pictures in this code. All right, so Hastings and Haw originally proposed this on the honeycomb lattice, but it can live on any plaquette three-colorable lattice. So a honeycomb lattice is just an example. Okay, so here's a honeycomb lattice. It's plaquette three-colorable, meaning we can assign a color to every plaquette such that no two adjacent plaquettes have the same color. I'll use red, green, and blue. Like so. And from the plaquette coloring, you can deduce a coloring of all the edges. So red edges connect red plaquettes, green edges connect green plaquettes, blue edges connect blue plaquettes. Along with this code comes a native set of measurements, which I'll just denote like so. And they're given by XX on the boundaries of the red edges. So an XX measurement here, for example. YY at the boundary of green edges. There's a green edge, for example. And ZZ at the boundary of blue edges.
Did you say where the qubits are?
I did not. Qubits live at vertices. And there's one qubit per vertex. Thank you. And please ask questions as I forget to say things. There are many experts in the audience. Okay, so what can you measure when you have access to these native measurements? One thing you can measure is the center of all the measurements. Okay. So the center of the measurements is generated by the following group. So red plaquettes with the product of X around the boundary, green plaquettes with the product of Y around the boundary, and blue plaquettes with the product of Z around the boundary. All right. And notice, in contrast to Tor code, the set of measurements that we're performing here do not commute. All right, so along with the set of measurements comes a measurement schedule. Schedule in this case is first measure the red checks, and then green, and then blue, and just keep repeating that. Okay, because these operators live in the center, once you've measured them, they survive forever. And so, okay, so then you can ask, how do you actually measure these? So if you follow this measurement sequence, what you'll find is if you measure red and then green, you will learn the blue plaquettes. If you measure green and then blue, you'll learn the red plaquettes. If you measure blue and then red, you'll learn the green plaquettes. Okay, and this goes on and on and on. And right, how do we see that? Well, it's useful to look at it in space-time. So what we're going to do is stand at the center of a blue plaquette and look at the world lines of the qubits on the outside of it. Okay, so I'll draw 6 world lines corresponding to the 6 vertices around the boundary of a blue plaquette. So I can even label them 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And around that blue plaquette, it's going to be surrounded by red and green edges. Okay, so let me draw those in. So here are red edges, and then here are green edges. Correspondingly, if we follow this measurement schedule, it's red, green, blue, red, green, blue. So here are the red measurements given by Pauli XX. Then we follow by green measurements, like so, given by YY. And then the blue measurements poke out of the plaquette. And then we repeat. Okay. And so what happens? Well, you measure XX on these 3 edges. Each XX operator will individually anti-commute with at least one of the subsequent measurements. So it gets booted out of the stabilizer group because of that. But the product of all these x's commutes with every one of the subsequent measurements. So that survives. So the product of XX survives. Then at this point, if you were to just leave it there, that product of x on all of these qubits will anti-commute with the z's, so it'll also get kicked out. But if you multiply it by the y measurements on the green edges, then it'll become the product of z here. So this would be an element in the stabilizer group at that time, and that freely commutes with these zz measurements. Once it commutes past, that zz gets measured again into the red and green edges. Okay? So here we learn the blue plaquette, and we learn the blue plaquette again here. You can then compare the values of those stabilizers and use that to perform error correction. So you get some minimum weight matching problem on a 3-dimensional graph. All right. Any questions? What time do I have until? Okay, great. All right. I hope I brought enough material. Okay, so
Welcome to stop early.
yeah, we will see. So well, I brought the draft of my papers so I could just start reading through it at some point. Okay, so yeah, that's the review of the Hastings-Haw code. Now, there's a very interesting observation made by these folks coming out of Berlin, Kesserling et al. And what they did is they connected the Hastings-Haw code to a parent code, the 2-dimensional color code. And they did this through the lens of anion condensation. Okay, so I want to review those results and then extend them. Okay, so yeah, the title of their paper is Anion Condensation in the Color Code. So I can just write that. Okay, so yeah, what is anion condensation, what is color code, and what is the connection to the Hastings-Hawk code? So first, the color code. So again, the color code lives on a Floquet three-colorable lattice. Again, exactly the same lattice as we have here, again with 1 qubit per vertex. Okay, the stabilizer group is given by the following. On every plaquette, you have the product of x around its boundary, and also on every plaquette, you have a product of z around its boundary. Again, this can live on any Floquet three-colorable lattice, and the fact that it's Floquet three-colorable guarantees you that these operators will commute. All right, so first, what is the connection to the Hastings-Hawk code? So if you were to look at all of the red edges and measure xx on those edges, which I will denote like so, you can just compute what stabilizer group you get. So let me call this, well, suggestively, I'll call it HH of RXX. So of course, you get the measurement in the stabilizer group that you just performed. So that's RXX. And then we can examine each plaquette operator individually. So here is a red plaquette. Sitting in that red plaquette, we had a product of z around it. That's going to anti-commute with RXX because the red edges poke out of the red plaquettes. We're measuring in the x basis. That's going to anti-commute with the z's. So this guy gets kicked out. The x stabilizer will commute with XX, so that survives. All right, now let's do the green plaquettes. So we have green. Around the boundary of a green plaquette is red edges, and they actually cover all vertices. We're measuring the red edges in the x basis, so the x plaquette at the boundary, the x operator at the boundary of the green plaquettes is already included in this part of the stabilizer group. So we don't need to discuss it. The z operator, it overlaps pairwise with all of the red measurements. So that actually commutes with this measurement. It will survive. So I'll put a product of z here. But because we have those red edges, I can multiply it by these x's that's already in the stabilizer group and write a product of y's. Okay, and I do that so it looks like the instantaneous stabilizer group of the Hastings-Hawk code. And then finally, for very similar reasons, if I look at the blue plaquettes, well, the z operator survives, and the x operator gets measured. So what one finds is exactly the instantaneous stabilizer group of the Hastings-Hawk code at the RXX step. Okay, if I did this for green YY or blue ZZ, you'd find exactly the same instantaneous stabilizer group as one gets out of the Hastings-Hawk code. It may not be standard nomenclature. Instantaneous stabilizer group is the stabilizer group you find after performing a set of measurements. All right, so how does this connect to anion condensation? All right, so there's a very convenient way to write down a generating set of logical operators for the color code. So let me title that color code logicals. And to get that, you write this table. You put the colors on the left and the Paulis across the top. And then every element of this table is going to be one logical operator. So Rx, Gy, Rx, Rz, Gx, Gy, Gz, Bx, By, Bz. Okay, how do those correspond to the logical operators? Well, for each color, you can choose a path along the lattice that connects plaquettes of that color, and then you can put the flavor of Pauli in this table. So for example, here is a path of plaquettes. I'm not going to draw the full lattice, of course. It's just a subset of it. Here are the red plaquettes that this path is connecting, and then the Rx logical is just going to be product of x's along that path. Okay, so this commutes with everything in the stabilizer group. It doesn't belong to the stabilizer group, therefore it's illogical. And it turns out that these generate all logicals. And for those that are familiar, the color code is sort of, as far as the anionic content goes, color code is equivalent to 2 copies of toric code, which is equivalent to 2 copies of the 3 fermion model. Okay, so there's 16 objects, 15 of them are non-trivial. All right, I should also tell you the fusion rules and the statistics. Well, actually, full statistics won't matter so much. It just matters whether they commute or anti-commute. Fusion rules are the following. So product of charges across a row fused to the identity. Product of charges across a column also fused to the identity. If you have a charge in a distinct row and column, they will braid non-trivially. If you have an object in the same row or same column, they will braid trivially. All right, is that all clear? Great. No?
Is that the easy way to see it's a 2-qubit toric code?
Easy way to see that it's 2 copies of toric code. From this table?
No, from the stabilizer.
Oh, from the stabilizer.
I know there's
Well, I could show, so we know, yeah, I guess I should have mentioned. Hastings-Hawk code is equivalent to a toric code. And I'm about to show you how you condense one object to get to toric code. It's FXZ2. You could invert it by gauging. That brings you another copy of toric code. Directly from the stabilizer group, I don't have a great way to see it. All right.
Sorry, I didn't understand. You said there were 16 objects, but then you pointed to that table with 9 entries.
These generate. So if you like, I can identify them with toric code.
No, it's 9 bosons. It's
9
9
bosons.
non-trivial bosons. That's probably easier.
Yeah, so if you want to identify with toric code, you can fill out the 4 outer corners like so, with the standard labeling of toric code, E, M, and psi, or E, M, and F, let's say. And then okay, so yeah, it's only the bosons. All right. Okay, so what is the connection to condensation? So over here, we took the stabilizer group of the color code, we measured RXX, and we found the Hastings-Hawk stabilizer group. Let's do the same thing over here and see what happens. So if I measure RXX, well, you know, this logical operator becomes trivialized. Or maybe in suggestive nomenclature, we say identified with the vacuum. Okay, so this trivializes the XX logical operator. These guys, yeah, let me just draw it as a table. RGB, X, Y, Z. And this is all still reviewing the results of Kesserling et al. So if you measure RXX, this guy gets trivialized, so I'll denote that with a box. These guys live in separate rows and columns, so they all get confined because they anti-commute with RXX, or the thing we're measuring. Confine, confine, confine. The objects in the same row or column commute with RXX, so they survive. But as I said earlier, the objects across a row all fuse to the identity, objects across the column all fuse to the identity. So GX and BX will be isomorphic via the condensate. And similarly, RY and RZ will be isomorphic via the condensate. Okay, so measuring RXX is equivalent to condensing the logical RXX. Well, logical Rx. Let me write it like that. All right. Okay, so now, yeah, using this condensation picture gives you a very convenient way to track logicals. So I'm going to write these 3 tables. but I'm not going to fill them out. I'm just going to use the same notation as over there. I'll write out what I'm measuring, and then I'll circle the objects that remain deconfined, and I'll leave out the objects that are confined. So in the first step, we have Rx. These two guys survive. The remaining ones get confined. At this step, we measure GY. Objects in the same row and column survive. The other ones get confined. And then we measure BZ. Objects in the same row and column survive. Everybody else gets confined. And then we repeat it. But let me actually draw this final step. Okay. And so the condensation is reversible, meaning it preserves the logical information if there exists a complete set of shared logical operators between each step. All right? So let's see how that works here. So suppose I'm following this guy. And yeah, let me use the notation. When we condense, I'll call this E tilde for the label of the E particle in the condensate. And I'll call this M tilde for label the M after we've condensed. Okay, so we have this E tilde here. And so it clearly commutes with GY. So it just survives. Now, if we look at what happens when we try to measure BZ, this object lands here, which anti-commutes, but it's isomorphic to an object that commutes. Okay, so we use that isomorphism. It survives over here, like so. Now commuting with BZ. And then again, this will anti-commute with Rx, because it's sitting here. So we can use an isomorphic copy of it, which sits here, and that will commute with Rx. Okay, so what we find is after one period, E tilde has switched into M tilde. Okay, and that's the automorphism of the Hastings-Hawk code. The dynamic automorphism codes will make use of this. We'll actually use these automorphisms in order to implement logical gates. We'll have a way to construct all Clifford gates and also a non-Clifford gate. Okay, any questions about this? You said 1215? 1240, 1220. Okay, great. Okay, so the idea of automorphism codes is sort of putting together these two ideas. We want to use a version of these Floquet codes, which implement non-trivial automorphisms, and we want to use this idea of condensation because it allows us to give very quick calculations. Okay, so for these automorphism codes, what we will do is start with a parent code, and I'll call it P. And then from P, we'll pick out a set of measurements, which we can call our native operations, available to us in hardware, ideally. And from there, we will measure those and find a series of child codes, all of which are described by the same topological code up to a finite depth circuit. Okay, so maybe we measure some operators M1, we find child code C1, M2, we find child code C2, C3, C4, C5, and so on. And then, so this is the, oh, yeah, sorry, I don't know why I wrote this, condensation graph. Okay, so vertices of the condensation graph will be labeled by measurements relative to an input parent code P. We will connect, so each one of these is a vertex in the graph. And then we will connect any pair of vertices if they share a complete set of logical operators. Okay. So that's, I'll draw the example of this graph in a moment. And I'll draw a bidirectional arrow, every time that happens. They won't all be connected. But that's an example. Okay, so now you can look at this graph, and one thing you'll immediately realize is that if you take a closed loop along this path, that will correspond to an automorphism. Okay, all the logical information is preserved along this loop, that's by definition, and it can undergo a non-trivial operation when it comes back to itself. All right, the trick is to find which loops are actually error correcting. Okay, that's the difficult computation. All right, so let's do an example. Example. And, well, as you can probably guess, the example is parent code is color code, and the child codes will be variants of the Hastings-Hawk code. So parent is color code. The set of native measurements that we're going to look at are the following. So you get to choose a color and a Pauli. In XYZ. So there's 9 options, meaning the graph should have 9 vertices. And it looks like the following. Let me also draw these in. RY, BZ, GX, RZ, GY, BX, GZ, RX, BY. Okay, so this is the condensation graph. It's on the 2 torus, so top is connected with the bottom, right is connected with left. And I've only drawn an edge between measurements when the transition is allowed, meaning it preserves all logical information. All right, so now I said paths in this are automorphisms. So let's pick a path. Here is one. So Rx, Gy, Bz, Rx, Gy, Bz, that's just the Hastings-Hawk code. Here is another example, just going through CSS measurements. I'll draw it with squiggly lines. Rx to Gz, Gz to Bx, Bx to Rz, Rz to Gx, Gx to Bz, and then back to Rx. That path is called the CSS honeycomb code, which was simultaneously discovered by Kesseling et al. And my collaborators, not with me. Okay, now it turns out any path that you take on here, doesn't have to be periodic, any path will determine, well, will be a quantum error correcting code with some non-zero threshold, conjecturally, if you traverse all 3 colors frequently enough. Okay? Right. All right. Another fact about this graph is if you look at the any homologically trivial loop, there'll be no automorphism. Any homologically non-trivial loop in Z2 will have a non-trivial automorphism. So the homology of the graph matches the automorphism of the code space.
Are you taking your path repeatedly? Like go
yes, so if you go around twice, you get a trivial automorphism.
But if I go like a random, then you still get an interesting code?
Yes, as long as you traverse 3 colors frequently enough. Yeah.
Well, if you don't traverse 3 colors, isn't everything topologically
It's trivial.
trivial?
Yeah. Yeah, exactly. If you don't traverse 3 colors, you're just going around the boundaries of one color type of plaquette, and so you get some, I guess, symmetry breaking order if you think in the physics language.
So I guess the question is the more important thing for generalizations of this is the path is topologically non-trivial, or the
I would say the error correcting aspect. Well, at least for my interest. Yeah, okay.
Maybe the same question. If you get a trivial loop, is that error detection?
It can still be error correcting. So let me give you an example. Here is one. RGB, GRB. In fact, that's the one that we use for gap boundaries. Well, Hastings and Haw proposed for with gap boundaries in their paper. Like effective distance it's extensive in system size. Let me say it that way. It is error correcting. Okay. All right. So now we can get to the sort of dynamic automorphism color code. 15 minutes. Perfect. All right, so this, again, sits on a Floquet three-colorable lattice. And now it has 2 qubits per site. And I'll think of those as layer indices, layer 1 and layer 2. Oh, I should give a title. Okay, so yeah, it's Floquet three-colorable, 2 qubits per site. The native measurements are now the following. So again, we get to choose a color, we get to choose a Pauli, and a layer index. So P is in Pauli, J is in 1 or 2. You can imagine generalizing to N if you like. In fact, we will in a moment. And then C is a color, red, green, or blue, all with the same notation as we've been using. And then Z1, Z2 is just a measurement that couples the 2 layers together. Okay, so right, so if I leave this out, it's then just the condensation graph is just 2 copies of this, which is just a product of cyclograph with 3 vertices. So if I want to draw the condensation graph, I'm going to struggle because it's in 4 dimensions, but let me sketch. So it's roughly, so condensation graph, it's a product of these 2 cyclographs with 3 vertices. And then we have this extra point given by Z1, Z2, which has some, non-trivial connections. So I won't draw what it looks like. All right. So, okay. Now, it turns out if you take the parent code, which is 2 copies of the color code, and measure any one of these objects, well, okay, you have to be careful. So if you're measuring the edges, you actually have to measure 2 distinct ones. If you're measuring the vertex, you just measure once. Each time you do that, you'll get to a child code, which is isomorphic to the color code. All right, what's an example? So take the parent code, and which is color code, and measure R x1, x1, G y2, y2. You will end up with Hastings-Haw code of R x1, x1 times Hastings-Haw code of G y2, y2. That's an example. This is just bilayer toric code up to finite depth circuit. Another example is measure Z1, Z2. And you'll find what I'll just call color code tilde. So measuring Z1, Z2, it identifies the Z stabilizers of the first layer with the Z stabilizers of the second layer, and it binds together the X stabilizers of the first layer with the X stabilizers of the second layer. Okay, so that's just a color code. And then these 2 vertices turn out to be locally reversible. Okay, so you could imagine writing a Mathematica script, which Nat actually did, to search over all possible paths here and compute what automorphisms are available to you. All right, so it turns out you can get all of them. And let me just say, sketch out what they are. So earlier I said color code is equivalent to 3 fermion times 3 fermion. It's known that 3 fermion has S3 permutation symmetry. Second copy also does. And then there's a layer interchange symmetry with Z2. And so automorphism group is just Z2 semi-direct S3 times S3. And it turns out every automorphism here can be realized by a path of measurements on this condensation graph. Moreover, every automorphism can be realized by an error-correcting path of measurements. So if you have any individual single qubit fault, you can detect and correct it. Okay, so that's one of the main results of our paper. But note, unfortunately, this is a subgroup of the Clifford group. It's isomorphic to this group. So even if you include n layers, you'll never get the full set of Clifford gates via traversing a condensation graph of this type. Okay, that wasn't our goal. We wanted to find a full Clifford quantum computer via a parent code, which is color code, and measurements of this flavor. And we do get to that by placing this dynamic automorphism color code on a triangle. All right, so let me just sketch that quickly. Actually, let me make sure. Okay. So, all right, so it's well known if you put the color code on a triangle with suitable boundary conditions, it has a transversal S gate and a transversal Hadamard, which both realize logical S and logical Hadamard. And because it's CSS, if you take n stacks of it, you will transversely realize C0 as well. And so you get the full Clifford group. Here we'll copy that. So we take the dynamic automorphism color code on n triangles, all stacked on top of one another. So 2n qubits per site. You then have to work out suitable boundary conditions, which are quite complicated in this case. But one can find suitable boundary conditions which are also error correcting. And when you do that, you find, or at least we found, the following generators of logical gates. So you find automorphisms which implement the following logical gates. S, oh wait, sorry, H, SH, and I swap. And just to remind you, H is this, S is 1I, and I swap is 1, 0, I, 0, 1. And this set of generators generates the full Clifford group. Okay. So just to maybe comment on that a little further. So one thing that is nice about this code is you can pick your logical circuit. It'll be some whatever circuit you like. You then compile it into Hadamards and SHs. From that, you'll determine a path of measurements to take, which will also allow you to simultaneously error correct. Okay. Another way of saying this is you get depth L logical gates in order L steps of measurement. All right. Any questions here?
The surface is just a triangle?
Yes. Yeah,
So if you want to scale to correct more than one error?
Oh, yeah. The distance is extensive in system size.
Yeah, system size is that n?
I didn't write it. So you again have like a Floquet three-colorable lattice sitting in the bulk here. And then you have a boundary condition which has all three colors running along the boundary. It's called a Pauli boundary. You can think of, there is a map that unfolds this into two copies of Torah code. Looks like that.
Can I ask a question? You mentioned that the automorphism proof of this particular graph can always be realized by these nice error correcting. Is that always the case, or is that something you have to prove every time you face it, or?
Exactly. You have to prove it every time you face it, and that's tricky to do.
And do you have a feeling that, so there is no recipe, it's just luck, or?
I don't want to say it's luck. There's an art to it.
Sure, because
that's the difficult part of it, figuring out which ones are error correcting.
Okay. Okay, it's art.
It's hard. You have to compute all the detectors and make sure, so sets of measurements which multiply to +1 and check that they detect a generating set of errors. When it's translation invariant, it's like, Margarita and Shankar have made code that actually could do this in a computer. So in the end, it was relatively efficient. Doing it by hand, which they originally did, is quite hard. Yeah, it would be nice if we had a way of, picking out condensation graphs which were error correcting. This is something we thought about for a while and could not do. In fact, if anybody can do this, that would be great. Okay, so in the remaining 4 minutes, let me talk about the three-dimensional dynamic automorphism color code. So, right. So the parent code in this case is 3 copies of the 3D color code rather than 2 copies of the 2D color code. And the three-dimensional color code lives on a volume 4-colorable lattice. So yeah, let me just write it. So 3D stack, and then it's volume 4-colorable. So we choose some cellulation. I will draw one 3-cell. And then we color each 3-cell of this lattice by the colors red, green, blue, or yellow, such that no 2 adjacent volumes have the same color. Okay? That volume 4 coloring induces a coloring of the edges in 2 cells. So similar to 2D, where the plaquette coloring induced a coloring of all the edges, here the volume coloring induces a coloring, a 4 coloring of the edges. It also induces a 2 coloring of the plaquettes. There are 2 ways to choose it. So if you look at a plaquette, it is neighboring 2 volumes. Say it's a yellow volume coming out into the room and a blue volume going back into the board. So we could happily label it blue or yellow, or you could label it by the 2 colors that go around the boundaries of the plaquette. It should be red, green, red, green, red, green, and so on. Okay, the stabilizer group is given by the following. So we, for every volume, we act with Pauli X around the boundary. That's 1 generator. And for every plaquette P, which is 2-colored, let me use BY, we multiply by Z around its boundary. The topological charges, well, single copy of color code is equivalent to 3 copies of 3D Tor code. An overcomplete set of generators looks like the following, logical generators. It's very similar to 2D. The string logicals are you choose a path along edges that connect volumes of a given color, but now you only have 1 flavor of Pauli. So there are 4 types there. RZ, GZ, BZ, YZ. And then there are 6 sort of natural generating membranes. So these are strings, membranes. You see I only have 1 minute. So membranes come with 2 color labels, and then Pauli labels fixed to X. GBX, GYX, and then BYX. Okay, and then of course, the strings all commute with themselves. The membranes all commute with themselves. A string anti-commutes with the membrane operator whenever they share the same color label. Okay, with just that information, you can work out what happens if you start measuring, say, RZZ. So along all the R edges, measure ZZ. You will condense this operator, and you'll confine any membrane that anti-commutes with it. If you measure a pair of these, you'll condense into a toric code, so on and so forth. So we started with 3 copies of 3D color code. We wrote down not all, but several condensation graphs, and found paths of measurements which can perform any of the color permutations in this model. So there's S4 of them. And then we also So similar to 2D color code, there's this transversal S gate realizing logical S gate. For the 3D color code, there's a transversal T gate that realizes a logical T gate. Well, it's manifold dependent. If you're on a tetrahedron, it's logical T. If you're on the 3 torus, it's logical CCZ. We also found a path of measurements, which again necessarily has to be non-Clifford, that allowed us to realize a non-Clifford logical gate, the 3D DACC. And so we combine that with a 2D code, and one can get a fully universal gate set purely by automorphism. Okay, with that, let me say thank you for your attention and take any questions.